Thank you. Thank you, everybody, for your time today and the invitation to come here. I don't know how groundbreaking this is. Sometimes it seems like a slow train to nowhere. But I'm going to talk to you today about what moves in the air and then leave you with a different way of thinking about things. So, great powdery mildew. All of you spend quite a bit of time trying to deal with it, manage it, and you really hope you don't see it. I love looking at it, but that's a different story. But first, let me give you a little bit of perspective here. I'm 2 meters tall, 6'7". That would make me the size of about a bacterium on a leaf. And that would make a powdery mildew spore about the size of a Goodyear blimp. This would be your average grape leaf. Notice Napa Valley in the center. Somewhere there is a Goodyear blimp. Can you find it? It's down in the lake. I tried to make it easy for you. But the reality is, this is the size, this is what we're trying to think of in terms of understanding how a pathogen moves. Oh, this would be an acre. Any chance of finding a spore? Actually, we do. And that's what I'm going to talk to you about. But this started way back in 1996 when I first moved out here from Alabama. Cotton, soybean, peanuts, that's what I worked with, coming out here to work on grapes. Yeah, some people think differently. But we were looking at disease forecasters initially. There was the Gubler-Thomas, the German model, New York model. And one of the things that we noticed was that they were all calling for sprays long before we ever found disease in the field. And I mean long before we ever found disease in the field. So that got me to thinking about the disease cycle. And I've tried to break it up here more like a computer programmer would think. I'm somewhat of a data geek. But looking at the different stages, and where's the laser pointer? What we have to understand with grape powdery mildew, it's an obligate parasite. It can only grow on a living host. So if the grape isn't out there, powdery mildew is not doing a whole lot. It's just kind of hanging out. It's hanging out as Cleistothecia, or if it's gotten into a bud, it might be living inside of a bud scale. Well, that's during the winter. Once we have plant emergence, we could potentially have the pathogen be able to start to grow. But one of the things we have to realize, Vitis vinifera and Aedes aegypti, they're both exotic organisms in an unusual environment. Neither one of them are native to the West Coast. And so they're reacting to the environment differently. And it's how they sense that environment that may give us a clue on how to manage it. But the other thing I want you to look at, grape powdery mildew has the potential of going through 35 generations in a single season. That would be the equivalent of this, the population in this room, becoming 2.9 times 10 to the 12th, or 2.9 trillion people all of a sudden in this room within a 9-month period. So think about how fast that organism is growing and how many spores are produced. So if we look at this, powdery mildew spore lands on a leaf. Within 2 hours, the plant has started to respond to it, and it's already germinating. At 5 days, it's reproduced. That's under optimal conditions. So it's a very fast disease cycle, and that's why you often say, well, the disease just exploded on me. Because it does have that appearance. But the reality is it doesn't just explode. There is a slow process in the early spring that starts to happen. But to understand that, we have to be able to find that spore. We have to be able to see it. Well, this is some of the work we started using a Burkhardt spore trap early on. This is number of spores, the hour of the day. This is Julian day, so 1 would be January 1st. And the number of spores across the hour of the day, but also across the calendar of when they're released. What I want you to really look at that, there's highs and there's lows of when spores are released. Now, this is us visually counting on a spore trap looking for grape powdery mildew spores. Now, I want anybody here to identify grape powdery mildew. It's actually this one down here. But that's only 8 spores. Imagine what's on one of these spore traps between all the dirt particles, the insect debris, everything else that's on a spore trap. It becomes darn near impossible to tell one of these spores apart, especially when they get a little dehydrated and shrivel up and look wrinkled and old. It becomes quite difficult. So we used, back in 2004, we started this. We started using the new information, the metagenomics that was coming on. And we made PCR markers that could separate out grape powdery mildew from other fungi. And then we began testing this. Could we actually detect spores that were in the environment? And our small research plots, if you look up here, the vertical lines indicate no detection, dashed indicates detection. Basically, we were only detecting in the early part of the season the pathogen when we had rain events. When we had a rain event greater than 1/10 of an inch of rain and 5 degrees Celsius or 50 degrees Fahrenheit. That's the only time we were detecting it. Well, that was a nice research tool, but me being who I am, sometimes I have stupid ideas that turn out, get lucky, and they come into something. I decided I wanted to look at this a little further, so I started building my own traps, because I'm also cheap. I didn't want to pay the $6,000 to $800 for the other types of traps, so pulled out my soldering iron and started building traps. Here we go. Whoops. Skipped a bunch of slides here. Anyway, to make a very long story short, we worked with numerous commercial vineyards. And over the time, what we got them to do was to hold back their initial fungicide spray until we got spore detection in their vineyard block. At 43 different vineyard locations over 7 years, they saved an average of 2.3 fungicide applications. We saw no difference, statistically no difference in disease control. 6 pounds per acre of fungicide. In Oregon, most of the early season fungicide is sulfur, so that adds up for a lot of AI. And if you look at these slides, you can see the red is no detection, green is when we got detection. We have growers' standard leaf program, so that's their standard disease management, whatever they chose. And then we got them to wait for the detection, and then we have the fruit infection out over here. Now, I should say this about the fruit infection. This is us under a microscope. You would never see this infection if you're just looking at fruit like this. We put it under a microscope so we could even see a single spore that had tried to penetrate the berry. And that's what we were calling infection on this. Visually, if we rated this, it'd be 0% incidence in these. But this is an interesting field right here, and I put this up for a reason, is this grower decided that entire 100-acre vineyard was going to be managed off that one spore trap. Had this much confidence in it the whole time. What we actually see here, the differences, is just an anomaly of where the disease epidemic happened to start. What we have growers do is put the spore traps where they had the highest disease pressure the year before. You find that by just scouting about this time of year, looking for the cane scarring. And the lower down on the cane that you see it, that's most likely the origin. So when you find the cane scarring, you just start circling around the vineyard, and you look for it closer to the exfoliating bark. Anyway, at this time, LAMP was becoming popular within the medical community for testing for malaria and other blood diseases. So we decided to try to employ it for growers to perform their own molecular detection at their desk, their kitchen sink. Yeah, we did have somebody working at the kitchen sink, in their winery, or even one guy did it out in his tool shed. But the extraction process is basically drop in the spore rods into liquid, boil it, take 5 microliters of that, transfer it in, incubate it at 65 degrees for 40 minutes, and then look for a positive or minus. It actually worked pretty good. We put this in growers' hands. 10 commercial vineyards, we put 3 traps. One, the grower did everything. They sampled the rods, they processed the sample, they did the LAMP reaction, interpreted the data, and then they made a decision on where to spray. 2 other traps we came in and monitored for comparisons. And in looking at this, the growers in year 1, they were about 55% sensitive at 1 and 10 spores. In year 2, we got them up to about 75. Largely, this is differences in how they store the master mix that causes this lack of sensitivity with the growers. Because us in the lab, where we have better equipment to store master mix, we could always consistently detect a single spore. But the growers, performed the assay. We compared it to the lab. In the lab, we have some difference in positives compared to our qPCR. The growers didn't perform quite as well. We were scratching our head trying to wonder about it. But then when we looked at the disease data, we're like, well, does this really matter? Because if we look at the disease levels in the grower-managed decision versus their normal, we see really no difference in disease development. They're able to make an accurate disease management decision using the tool, even though there's a fair bit of inconsistency within the detection technique. Well, part of that is in dealing with how we have them sample. We have them sample every 4 days. The optimal, the best generation time you could have for the pathogen is 5. So they have 2 opportunities within a time to make a management decision. So if you get a false negative or a false positive, there's time to recover from it early on. And actually earlier on in the season, you probably have a 15 to 21 day in between a generation. But the reality is they could make management decisions. Now gave us an idea. One grower decided during the time of season, he was actually going to start messing around with spray intervals based on the data we were giving him. And for 2 years, it actually worked. So we decided to come out and we tested it at commercial vineyards, got each grower to set aside 2 blocks. One where they managed their normal program, one where they adjusted the spray interval based on the number of spores that they were trapping. So these are the different vineyard sites, the number of spores that were being trapped, and here's the disease development. And I've got 2 curves for this year. One is this particular vineyard decided to go off reservation and not put the trap where we told them to. So they put it where it was convenient to pull up with the truck, take the sample, jump back in the truck, and process it, instead of where the disease hotspot was. And so the epidemic got a little bit out of hand with them. Everybody else put it in the disease hotspot, and here's how we see their control, which is green, what they normally do, and the modified spray interval. They were able to measure it. And in both of these systems, or in all these growers, one grower was actually 4 applications difference, and the lowest was 1 application with an average of about 2 application difference in savings. Now in California, I know working with Seth Schweb's with Coastal Viticultural Consultants, he's actually had several people increase the number of applications that they've made based on using the spore data. And in doing that, though, they've significantly improved their disease management because they actually weren't starting their management program early enough. So this is looking at daily spore loads and comparing to where we see across 4 years here, where, boy, I'm having a hard time seeing what we're... The diamond is inoculum when detection occurred, and the square is when bud break. What I'm trying to show you here is that it's more important, there's more to the disease epidemic and the pressure of the disease than just when it starts. And this is where we're going now. Can we predict the spatial distribution of disease? Can we tell you exactly what row, what part of the vineyard disease severity is going to be developing in the most intense, or what risk? If you think about it in Willamette Valley of Oregon, we often have 2-day spray interval because it's too rainy to spray, too wet to get the tractors in, and then you've got 100 acres, but you can only do 10 acres a day. Where are you putting those tractors? You want to know the disease risk. And this is some of what we've been doing. We take climate data, working with Chris Daly, Prism Group. There's a number of organizations involved in this research. We ingest 16,000 weather stations across the United States, interpolate the data based on aspects of geography. So what altitude, what's the slope, what face is it, and then we make a prediction. If you look here, this blue line is the historical interpolated data, and then the pink line here is we're projecting forward, because how many of you can go back in time to do something? I can't. I try. My bosses think I can. But we're trying to give you predicting forward. If you look at a disease risk, if you're looking at today, the Gubler-Thomas index, say, was at 20, but you saw in 7 days it was going to be at 100, you would make a different management decision than if you looked out and saw in 7 days it was going to be at 0, wouldn't you? So we're trying to add prediction to all this, real prediction. A lot of what people call disease forecasting is just saying, you know what happened yesterday? You should have been on your tractor. Not very helpful. And if you watch, I hope it quit running already. I had a little map right here. This is some of the spatial. You can go online to right here, and this is actually running where we spatialize out the Goobler-Thomas index to look like a weather radar map for you. And we're actually trying to get down to smaller scales. And this is how this performs. What we did was interpolate data. You can go onto this site and pick a weather station anywhere you want. It doesn't matter whether there's weather data anywhere near you. We interpolate that data down to that spot, and we call it a virtual weather station. And if you look here, we have our virtual weather Goobler-Thomas and are measured at that site. Not a lot of difference. And then we actually, at these locations, we ran an untreated control. We did the green is untreated control, a standard calendar program, the Goobler-Thomas and the virtual Goobler-Thomas, and this is the number of applications that were made with each of those from that site specific. And then here's the disease curves that were developed. And one thing about untreated controls, if anybody tells you they compares their product, fungicide product, to an untreated control, and they haven't done a water control or a surfactant, just move on. Because 9 times out of 10, the surfactant or the water is your active ingredient when you're dealing with something that has marginal control. I found that with many products that the surfactant was what was active. AQ10 being one of them for years. So where are we going with this? The assumptions of the current forecasters. Sporulation is always occurring. Probability of infection is equal throughout the vineyard. And growers can react. You try to react, but the reality is the tools you have to be proactive. So we look at sporulation. This is some new data from David Godoy. Conidia matures in the morning, so it becomes available for release in the morning, and only one spore is produced. And once that's released, there aren't any more available. So if we think about that, we have to start understanding when that spore is moving and where it's moving. Well, I teamed up with a group of engineers that DOD really liked to fund how anthrax moved through Washington, D.C. So we actually took these models and are now trying to apply it to an agriculture environment. Using these type of models, we created vineyard rows, and this is all in theory now, but notice this red area, how this foci elongates over here. The wind is actually moving at a 45 degrees over here. This is a phenomenon that I've noticed for years and years in vineyards, is the foci are elongated along the row. I always thought it was tractor movement, people moving up and down the rows. But actually what it is air turbulence. And I'll show you here. This is one powdery mildew spore caught in air turbulence. And notice right here, it gets down in the vineyard and it's slowing down. And it looks like it's wiggling, right? How many of you watched a river flow or on a rock sitting there and the eddy that forms behind that rock and just holds things in it? That's what's happening in the vineyard. We get these eddy formations, and that's affecting how the pathogen disperses. How do we know that's right? Well, this is our field experiment. This year we had a 10-meter tower. Well, actually in this location there's $500,000 worth of equipment right now. Thermal imaging camera, DTS, all kinds of equipment. But to understand how particles move, what we release are fluorescent microspheres that act as surrogate spores. They're nice because you can see the different colors. And you look, that's the particles. We can release trillions in a second. It makes it a little bit easier to find and track and quantify. But what these experiments are starting to show us is that as we get vineyards tighter and tighter together, they behave more like a flat surface as the rows get tighter together. As they get further apart, you start to get eddy formation, elongation of disease foci. Disease foci, or think of mealybugs. They're just a 200 micron particle. They move just like the powdery mildew spore. How many of you notice that mealybugs tend to move down a row, but also skip vines? Our models actually explain that. Okay, so here's just one of the profiles where we're going. We see the same type of thing, but this is where we're trying to end. We've got this crazy idea right now. VitSim, simulation environment for vineyards. Now, first of all, I want to give you this famous quote by George Box. All models are wrong. Some are useful. Question is, can we build something useful? Fact is, it doesn't actually seem to matter how accurate a lot of models are. Take SimCity. How many of you think that works for a city? It didn't predict a darn thing for a city. But what the research has shown, it's a brilliant tool for teaching how to make a decision, how to make a fast, accurate decision off incomplete information. Can we build that type of tool in viticulture? If you watch this is a GPU model of sun rays hitting a statistically accurate grape canopy, three-dimensional. We can run this faster than real time for a 2-acre vineyard right now with each individual leaf model. And here's what we can start to use it for. This is temperature, and you'll start to watch the leaves warm up as the day goes by, and we can translate that to evapotranspiration for each leaf. Now, these are crude models right now. They're not as sophisticated. I had noticed this morning there were a couple of talks that I need to incorporate some data from. But the group that we're doing with, this is Brian Bailey's work, a PhD students here. We're getting there. We're getting there slowly. But this is why, as Greg pointed out, the areas for habitable viticulture or viticulture as we understand it right now are changing. And they will change in the future. And imagine a simulation environment that helps you make decisions now for where to move and how to build your vineyards. Because we all know it takes 10 or more years to build something that gives you a decent wine, right? So this is my group. We're waiting for the wind to blow so we can do release experiments. Number of cooperators, a ton of growers that have risked a whole lot more than I care to think about, and our funding agencies. So questions? I think I have a minute or so for it. I'm Scottish, by the way.
Any questions? No. Thank you very much.
Thank you.